So, hi, John. Let's see, the actual class is going to start in like 5 minutes, but I have to run and run a faculty senate meeting. So hopefully it'll be a good class.
Hey, what's going on?
How much?
Yeah, so apparently, they're having this little like award they're giving out to the staff, and no one at UAF has been nominated, and it's due on the 12th. But if we get a bunch of letters saying like, "Oh, Connie,
Were we nominated? Oh,
Connie does a
everything.
bunch for us," and
Everything.
it would be, if she wins, that's awesome. Also, if she doesn't win and just gets nominated, that's still something that she can talk about, right? Because apparently she gets some flack from like the ministerial, yeah. So having some stuff in there saying like, "Hey, Connie helps us all out."
Why are my gloves? I didn't bring my gloves.
So yeah, you can. She was even
I
like,
can do that.
they said that
I can send
you
you.
could like just do like a paragraph or something. I think it
Can I
should
do
be
this
that.
online?
I think we have to like package it all together. So if you just want to send me an email or
Okay.
something, I'll
I'll
do
write a
that.
letter and send.
But yeah, it can be like short. If you just want to make a paragraph, or you could make it better than that. We expect much from you, and because you're the only English person.
I'm not the
You're the
only
guest.
English.
Yeah.
I'm not even English. I'm American.
You're the only published author. in the
That's not true.
department.
All of the professors.
That's true.
All right, so I guess I gotta call John.
Oh, you can just put a thing in there.
A thing in there.
You have a computer with a Ethernet dongle.
Oh, we do. So
Is John here?
I'm trying to
Not
figure that out. I have an invite from Lawler. I don't know how long ago this was. That's literally.
Was John not going to be here? We were just going to
I
record
think
it for
we're
him.
recording it for him.
Are we? So this is already being recorded. Everything.
Is it being recorded?
I presume you set this up so that it is.
Stop broadcast live.
So I think you don't want to push that button. I think everything else is good.
Okay.
All right.
That's broadcast though.
Yeah, because the broadcast records,
Okay.
so it can be viewed later.
Got
it. I think that's
That's not
what's up.
at all.
But
All right. Then all that work I did was kind of
Here, I want to get this out of here.
This is telling me. Great. All right. So today we're doing the pumping lemma, which I don't know if I will actually fill up the whole time because the pumping lemma is kind of simple and I wish we had a little bit more about it, but I'll try and do what I can. So first, we were talking specifically about for regular there's a pumping lemma for context-free languages, but we don't, I guess, talk about it. It's basically the same. I'm not sure the proof's the same, but the actual lemma is the same. And that you can split up a string in a context-free language into enough parts that you can then pump those parts. But it's a little bit more complicated. Okay. I actually have to pick this up and write stuff. I printed off notes and then just left them in my office because I'm smart that way.
Good job, Ben. Good job.
Let L be a regular language. Then there is an integer. We'll call it n. words in the language in L. We'll actually use this symbol. Is greater than or equal to n. The following conditions apply. First, we can decompose W into X, Y, Z. Second, X, Y is less than or equal to N. Y is greater than 0. That's not a greater than symbol at all. This is not what I wanted at all. And then X, this is the real bit that's interesting. Greater than or equal to 0. Yeah. Okay, so the intuition here is that, and we'll get into it more after the formal proof, but this part of the language, or the string, the word, is what we're going to be pumping over and over again to produce a string that's in the language. So let's say we have, just trivially, a star as our regular expression, our regular language. Then we can break up, say, a word A into X, Y, Z, and then we can pump the Y to A, and so on. I didn't quite, I sort of knew this, but I didn't really like sort of consciously realize it. The pumping lemma is also the sucking lemma. So you can actually delete the A here. It can be 0 or more. So this can also be pumped or sucked into AA, which I didn't really think of. It's almost probably never used, but I guess you can use it in a proof to show that I can't suck this part out of the language, therefore it's not, or out of the word, so it can't be regular. But I think it would be hard to prove that. All right, formal proof, and I'll write some stuff up again, or formal or proof, I guess. This isn't really a math class, so.
What's the end at formal?
Formal-ish.
Okay, got
Formal-ish.
it.
Because there's
But
an actual.
formal is proof.
There's several mathematicians in here, and I don't want to do. I've learned that I'm not as
Rigorous?
yes, exactly as I thought I was in the past. Suppose we have which is regular L. I should just keep this with me. Then we can, because it is regular, there's a machine which is the DFA which any string in okay. Am I boring you, Eric? Am I boring you, Eric?
No. I need to get more oxygen to my brain to really
Good
understand.
call.
Nice.
Okay, so that machine is a DFA. We all know what DFAs look like. They look like this, right? Or just they have an A on them. That means they do this thing. Okay. So we have chosen now then to be the same as before. Some W whose size is greater than n. We choose n, so machine M has some number of states. We'll call it M, little m, and we choose n to equal m plus 1, right? So the length of the word in the language we're examining is equal to n. Yep.
Hang on a second. You need to say what n is.
N is,
You already said. Okay.
yeah, n is the,
but saying what n is comes before saying w is at least n, because it doesn't make sense to talk about n to say what it was.
oh yeah, good point. I completely messed that up. My bad. So this is the actual statement that I want, right? We're actually going to do this. Exactly equal to m. And we've chosen n, we're chosen w to be that size, okay? For some generic language. So then we can sort of imagine as we go through the DFA, call it state 1 or Q0, that's what I use in the notes, Q1, all the way up to Q n minus 1 to Q n, right? This is the path it would take when I was going through the state machine to become accepted, correct? And this would be an accepting state. So there are n states on this path, right? Everyone sort of get that? Because there are n states on this path, and there are only m states in the machine, and n is defined to be larger than m, there must be a repeated state somewhere in this path. We'll call that state Q sub I.
This isn't really a problem, but there are actually n plus 1 states on the path.
Because you've got.
Oh, did I?
1 through n and then 0.
Yes.
And so I mean, it's n can be m.
Yeah.
For that reason.
If I change it to that, does it fix it?
What?
If I change the 0 to a 1 there, and then so on.
I'm saying you can set n equal to m.
Oh, can you? Okay.
Yeah, that's why.
Okay.
That's why we call it. You know, you don't need the separate letters. If you start somewhere and do n transitions, then you hit n plus 1.
Oh, okay.
States.
I just did this because I know this is the case.
Yeah,
and I didn't worry about it.
anything m or bigger works.
Yeah.
But m works.
I do this because I'm stupid.
Okay.
Because I'm not a mathematician and I
Right.
don't realize this
Right.
trivial thing.
Sure, it's no problem.
So then there's a state, some state Q, let's say QI. That's not a Q. That's not a Q either. That was a Q before, and these are all whatever. That comes down here, then loops through some series of other transitions, maybe, and then goes to here. So we can think of characters from here to here as being in Y, right? Being when we take W and make it X, Y, Z, this would be the portion of the string we count as Y, right? So it's clear then, because it's a regular expression, that we can extend Y. We can just make, we can extend it to be X, Y, Y, Z, and it would just do this loop twice. Likewise, we can do X, Y, or X, Z, and do this loop with none, right? We can just there's a word for cutting a path that I don't recall. Cutting cycles out of a path that maybe I'm crazy about that. I thought there was. Point is, we can
Excise.
we can skip. We can skip this cycle altogether. So we can do this clearly n times, or let's say, let's say j times. We can clearly do this j times, right? So we can construct a word that will, we construct a word like this. Therefore, the language is regular. there exists the pumping lemma, right? The pumping lemma. Not as formal as maybe it could have been. I'm sorry. But I think it's really intuitive, and anything else that I missed was more details, or sort of unimportant details. Is that clear? Anyone got any questions? No? Nah? Because I'm about to erase all this and go to like implications. Okay. Okay. So implications. The big one, of course, is that the pumping lemma
Would you like
You
to?
can't prove a language is regular.
you can't prove a language is regular using the pumping lemma.
Deciphered your handwriting.
I'm so sorry. I should say these words out as I'm doing them. I know it's a problem.
You
It
can also.
can prove a is not regular. Is that slightly better? Did I do better there?
You did do better there. I think you can still do even better though.
Yes, I believe I
Confidence
can.
in you.
So it can prove that language is not regular by constructing a word in that language that cannot be pumped, that is above the length required. So I guess it needs to be just any length. I don't know about that. So let's do some examples, some trivial examples. The famous ones are A to the N, B to the N is the language. I guess if we're being strict, we'll do that. So trivially, we can imagine X. We can just find any word, right? That would be in this language that couldn't be pumped. So we can do A, B, B, B. Take X to be this, or Y to be this. X and Z. And we can clearly show that if we pump Y, I mean, literally just by looking at it, that this is not in the language because it becomes A, B, A's precede, or B's precede A's. B's precede A's, and that's not in the language. A more interesting one.
Can just mention you don't get to pick Y.
I don't.
Yeah.
Oh.
Okay.
So I can.
So if you're really going to prove that language isn't regular, you need to show that there isn't any Y. You can pump.
Okay.
So
I can do that. It's pretty simple. I did it last time. But let's say we pick. So let's say we pick Y to be all A's, right? Then, we pick Y's to be all A's. Then there'll be more A's than B's when we pump. We pick it to be B's, all B's. Then there'll be more B's than A's than when we pump. And any mix of the other will precede B's with A's. But it's good to know that it's a little more complicated than that. Okay. I don't want to do that. The example I wrote up, I left my notes downstairs. Actually, no, I probably could do it. Because I'm ready to do it. So let's do another example. L is equal to 0, I, such that I is prime. Yeah. This is a little bit less trivial, I guess. It's not really clear as to how to do this, but we can start, okay? So let's take W to equal 0, I think, M. Where M is a prime larger than N. this. Then we can break up W into X, Y, and Z, which is equal to 0 times the size of X times 0, which this being concatenation. So I guess we're playing fast and loose with notation at this moment, but okay.
And is that where X, Y? Okay, no,
Yeah, these are the sizes of X, Y's, and Z's. Okay.
Yep.
So when we pump Y, let me think about this for a bit. Yeah, no, we get it's the other way. So if we take our word to be, the proof I found of this online did this, and you guys can tell me if I'm wrong or not, because I'm not as critical as maybe some other people. They took X to equal Y, right?
I don't think you need to.
So then you can do,
I mean, you don't get to pick Y, so.
yeah,
I don't think it's a problem. I mean, suppose you pump Y, what number does that represent? Can you make it be a non-prime?
oh, definitely, right? It's not necessarily a prime, right?
Well, if it isn't, well, that's what you need to show.
Yeah.
But you can always pump a prime to get a non-prime, and so you pump something and it's not in the language.
So this would be Y, this would be 2Y, for example, because we pumped it. Right.
Or KY or something.
Yeah, so we'll do KY. Then the length of W is equal to X plus 2Y plus C.
KY.
KY, yeah.
Well, if you can pick a K for which that isn't a prime, then you're done.
Yeah. Of course, to do that for any, I mean, there's probably some proof that says this.
What?
There's probably some proof that says this.
Some
There's some proof that says this is almost certainly not prime.
Well, it's
Yeah.
It's pretty easy. Take the length of the original W plus 1.
Yeah.
I think make that your K.
Yeah.
And then your number is your original W plus
the
original W times the length of Y, which is divisible by the original length, the original W, and so it's not prime.
Yeah.
Does
That sounds right.
that make sense?
Yes.
Let K be the length of the original W plus 1.
Okay. Then we have which is equal to, we'll erase that, which is equal to
Those are.
I mean,
I don't know what that says.
oh. No, hold on. This is that, that's the bar notation gets a little, I'm sorry. X. Yeah, okay. You're laughing at my handwriting again? I see how it is.
Yeah.
I don't know. I can see how this is not necessarily prime, but I don't see.
Well, X plus Y plus C is W.
Yeah, that's true.
You don't have to show that it's all prime or all not prime. You just have to show that some
Yeah.
are not,
Yeah.
right?
There it is. Yeah, well, that's some, in particular, K is the length of W plus 1. Then you get, what do you get?
Well, prime.
You get the length of Y plus 1 times the length of W. Those are both numbers bigger than 1.
Yeah.
You multiply together two numbers bigger than 1, you do not get a prime.
That's pretty much what the proof was, I saw. But it just let x and y be 0 or equal, and then you could factor and actually produce the two factors that were the prime. So yeah, that was rough. I'm sorry, but that's why you can't use a regex to find primes, because otherwise this would be the length of, you could just find primes using a regex. Okay. And of course this thing goes to sleep all the time.
I wondered, just a thought, I don't mean to interrupt you.
No, go ahead.
Go ahead after this, but when you're done, why don't we at least look up the pumping lemma for context-free languages?
Sure thing.
And we don't have to prove it.
Yeah, no, I actually have it open on Wikipedia because I wanted to talk about it, but that's actually everything I had.
Can we see a regular that, like, it's not proven that it's regular, but what happens with the pumping lemma in a regular one?
So write down a regular expression.
Yes.
Any rate, literally any one. Let's do, I did A star before.
Yeah.
But we could do A star, B star. Any number of A's, any number of B's.
Yeah.
Right. In contrast to the earlier example, to this example. So we can choose our W to be, so we can choose X. Well, we can't choose X, but we can, we can talk through this, okay? So we choose our A's to be all A's, then we can pump it.
Okay. Because you can have 0 B's in there.
Yeah.
Yeah.
You can have any number. If you choose our Y to be all B's, then we can pump it.
For the same reason.
But then if we do Y is A's and B's, then you pump it, and then you don't get actually something in language. But A's can be zeros? I don't know. I think you get to choose your Y. I think you have to be able to choose your Y.
If you're proving that it's not regular, you have to show that it doesn't work for all y.
Yeah, but
If
so
it's regular, it just has to work for some.
for some?
Yeah.
Okay. Yeah, you're right. I get what you're saying. Yeah, there are some Y that this doesn't work. Thank you.
Okay.
Right?
No, I don't quite follow that.
Let's see. Maybe it's
Well, the pumping lemma says there is a y that makes it work.
Yeah.
Okay,
Not that
got
every
it,
Y makes
got
it
it,
work.
got it. So if you show a Y that makes it work, then you're
It is
good.
the
If you
composite.
don't, if you
If there
can't
is
show a
no
Y,
Y
then
that
you
makes
show
it
that
work.
it's not regular. Yeah, no,
You're right.
okay, that is easy. I don't know why that was.
It's really,
escaping me.
it gets really,
Yeah.
Gotta be careful. You're familiar with the notion of something being vacuously true.
yeah.
A statement about all items in a set is true if the set is empty. So a statement about all strings with length at least n is true if there are no strings of length at least n.
So the
And
example,
so if we have a regular language that does not have arbitrarily long strings, we
For
just apply the pumping lemma by setting n to be huge, and then there is no w, and hey, they all can be pumped. Okay? So,
that makes a lot of sense, because I was kind of wondering, this is clearly a regular language. ABC is clearly regular. Nothing else allowed, right?
so let n be 500.
8 and B4, right?
N be 4, sure.
Yeah. And there are no strings in the language that are allowed. Okay, that's cool. So let's do the regular link, or the context free, which I might have misspoke. It might be something other than context free, but I don't think it is. For context free languages, that was correct. So formal statements, I'm going to erase all this. Is that okay? Okay, nobody said no. We don't do enthusiastic consent here in the CS department, apparently.
You missed an eraser.
There's like a B star or something.
It looks like it was that. You got part of it.
To write down the formal statement, and I'm not.
Transformation.
So L is context free. Then
Wait, what was that T word that you just did? Is that there?
There.
Okay.
Then there is
P greater than or equal to
1. For every S is greater than or equal to P. Then can be written as UVX UVX UVW XY is how they do this. And yeah. Oh, 0. Okay.
So is that the size of VWX and then UY?
Oh, whoops. I totally did not write the P. This is VUI.
So UWX and then VY.
Nope, both V.
Okay.
Here, let me go through and edit this. So that all the U's are U's. Yeah, that's it. I'm done. So you can see it's pretty similar. They have a diagram here that shows it a little bit better. I don't know if you want to go look at it. When we do context free, we can find, I think the basic intuition is that we have some start symbol, then we have some terminals A, some terminal B, these other terminals, and finally some more terminals. This A can always be expanded as many times as this A and this B can basically be expanded a bunch of times. It's sort of the intuition. This isn't, I wouldn't claim this formal or even convincing, but that's sort of, I think, what they're trying to get at.
Just intuitive thought. If you have a context-free language that has arbitrarily long strings, and
Yes.
there's some bunch of strings that function as a left parenthesis and a right parenthesis.
Yeah. Yeah, exactly.
And you can add more of them.
Yep. That's it.
Ah, I see.
And this went significantly less long than I wanted it to. I guess it's a pumping one for you. Nothing's really interesting.
What's that?
I guess it's pumping one.
So I kind of have a notation question.
Yeah.
Why is there the absolute value sign around the S?
That's just size of sets, cardinality of a set.
Okay, got it.
Yeah.
Got
I
it.
guess is the.
Set theory stuff. Okay.
Yeah.
It's not represented.
Is it that? Don't.
I think it's just representing the length of the string.
This is generally
Like the
because
strings,
well in
Putting-
vectors, right? These
From the size.
that's magnitude. It's a general
Okay.
thing for size.
Yeah, okay.
Right. Not always. I mean, I guess absolute value kind of thinks of the size, the absolute magnitude of a number.
Yeah, it's just
It gets very confusing when you have parentheses around it. I agree.
yes.
Yeah. Any comments on the pumping llama? Any softball questions?
Do you have something else to say?
Not really.
Okay. You know, there's another standard example of a language you can prove is not context-free.
Which
With
is
this, it's A to the N, B to the N, C to the N.
oh this thing with this one.
A to the N, B to the N, C to the N doesn't satisfy this. Just like A to the N, B to the N isn't regular because it doesn't satisfy pumping them for regular languages. And that's
Yeah, I can see that. Very.
that's a pretty darn simple
Yeah.
language,
Because
really. So, but
It's lower down on the Wikipedia page.
is it?
Yep.
I. Oh, it is.
it's a bit painful to apply it. But no matter how you bust that in parts. You can't.
Well, you can sort of just see it. I mean, that's the pumping lemma, and that's the pumping lemma, right? So you split this in half, right? You do that, pumping lemma on that side, pumping for regular languages on this side, regular languages for that side. And then that, at least to me, gets you 90% of the way, or maybe all the way, right, to the proof.
Oh yeah, maybe this is easier. Yeah. So if
Right, because you can
if you
show
want to
that.
get a big string, it's got to have A's, B's, and C's in it.
Yeah.
The only way to do that is to have like V contain
A's
either
and
one of
B's.
those strings contains A's, B's, and C's, and
Uh-huh.
then you'll get ABC, and that's
Yeah.
not good. Or one string contains A's and B's, and the other contains C's,
Mhm.
and then you get BA. Or one string contains A's, and the other contains B's and C's, and then you get BC.
Yeah.
Yeah. Okay.
Yeah.
Sure.
That's what it seems like to me. Yes. So yeah, pumping lemma. It's important to show that. I think we use it a lot more later in the book to show that, to show that you can do things. To show that languages are not languages, or the languages that are regular are not regular.
Languages.
I forgot.
Yeah.
No, I did say. Did I say the pigeonhole principle this time? Dang it! That was my one goal for this class, was to say pigeonhole principle.
Well, you said it.
Yeah, now I have. You can do the pumping lemma. The whole the reason why you repeat states is the pigeonhole principle. Right.
But you have to talk about the pigeonhole principle and understand it. Or?
I understand it. No, during the proof of the pumping lemma, you use the pigeonhole principle to show that a state was repeated. And I wanted to say pigeonhole principle. We're like, oh, we finally used it in its explicit form here, but I completely forgot because it's so easy to just implicitly say, clearly this is the way it is, right? Okay. Yeah, sorry. This chapter's 3 pages. I'm not joking. I can't help that the pumping lemma is 91 to 90. Oh, I might be wrong. It might be 4 pages.
Oh, yeah. That's
91.
33% larger.
91 to 95. Thank you. 4 pages.
Can I throw something at you here?
Sure thing.
Okay. What? Back to the regular languages.
Okay.
What's it good for?
War.
So I've been made an excellent point that you cannot use it to prove a language is regular. That would be the converse. Actually, I'm wondering about that. I'm not. I hope I know at least enough about this to teach it because I have taught it, but it's not really my field of expertise. Surely, if the converse of the pumping lemma were true, somebody would say so. But
Yeah.
nobody ever does. So presumably, there's a language that's pumpable but not regular.
You could find
Right? Otherwise, the converse would be true. So I'm
I
not
think you
sure
have to-
what that would be, but I don't know.
well.
But anyway, what?
So by the Chomsky
Oh.
hierarchy, right? By the Chomsky hierarchy, if you can pump it, then it's a regular language. Well, no, hold on. Never mind.
No,
Let me-
apparently not.
let me-
Otherwise, they'd put an if and only if in the pumping lemma.
I had
but
that backwards,
I mean, that's just a
Yeah.
proof by it isn't in the textbook, which
Yeah.
is not a very good way to put it
Yeah.
in proof. But I mean,
Okay.
it seems reasonable.
Converse of lemma not true.
Yeah, it's on
For
Wikipedia.
example, consider the language L, where
Oh, this is really bad.
yeah, this is terrible.
Yeah,
This is
it's
not
like
a
really
great-
formal and stuffy.
Full of notation and whatnot.
Yeah,
Yes.
and they use this really pathological
I don't
example.
have a laptop. Where are we?
This guy. I was hoping it'd be some easy thing like
No, it's really pathological and not, well, maybe not pathological, but it's really like, I mean, it feels like it. They construct a language out of 3 different.
In other words, L contains all strings of the operator 0, 1, 2, 3 with a substring of length 3 as a duplicate character. as well as all strings over this alphabet where precisely 1/7 of the string's characters are trees.
So here's a better example.
Okay, well, here, well, I'll get back to that.
Let me write up a really quick example of one that you can pump if you choose your string wrong, but is not regular, right? So L Y such that Y is in 1 clean star. So this can't be this is not regular, but you can choose a set. You can choose a word in this language that is pumpable.
Not sure I believe that.
That's pumpable.
Yeah.
It's not pumpable for all words, but you can choose a word. You can choose a word in the language to be pumped.
Well, but it's all words above a certain length they're supposed to be. That's what I mean by pumpable.
Okay, well, never mind. I guess.
Well, yeah. Okay, so there are languages that are pumpable but not regular.
Wait, isn't it at least one would be not regular?
The pumping lemma does give us non-regular languages. Okay, with,
Yeah.
A to the N, B to the N being the standard example. Oh, think about this. I'm going to make a language. Okay. So another AB on the beginning, just for the fun of it. Okay. Okay, so a language that consists of AB, and then all strings of length at least one that are only A's.
So A plus.
Okay, that's regular because here's a regular expression for it. Okay. So it must be regular. But there isn't any way that I can pump that string. Okay? Anything I do with that string to pump it is going to make a longer string that contains both A's and B's. That's not going to be in the language. So, what does that tell us?
Tells us that we need to pick our
What?
N to be. Tells us we need to pick our N to be large.
Okay, and
Yeah.
N is the number of states
Yeah.
in automata. So this language cannot be recognized by a six-state DFA.
Oh
Okay,
yeah.
so any DFA recognizing what I call an L must have at least 7 states. Which I don't know. That you know, just off the top of my head, that doesn't look right. I think that's a really simple language. I could probably recognize it in less than 7 states, but no, you can't. I don't know. Maybe it does look right to you. It doesn't look right to me, but it's true.
Because if you try and simplify it anymore, you're not just gonna be left with
Because
the
whenever you have a non-pumpable string of a certain length,
You have that literally that that
Yeah.
list of
Yeah.
of states, right? If you had any, you have that literal list of states, right?
Because if you do AB, you must do AB.
Yeah, actually
Yeah,
doing the 7-state automaton for this thing would be pretty straightforward, right? I mean, you got A, B, A. I don't want to do others. I don't know. And there's my accepting state, and then I'll have another one out here, which is, oh, and that's an accepting state too. How many state? 1, 2, 3, 4, 5, 6, 7, 8. Can I do it with 7?
So why is the
Sorry?
first B an accepting state?
First, the empty string isn't in the language.
Yeah. So you start there, you take an A, it's accepting, and then you can go down on another A and then transition again.
It doesn't mean I can do it in 7 states, but I mean that means I can't do it in less. So that is 8 states. That's probably a minimum.
Well, this is an NFA.
Sorry?
This is an NFA to be strictly speaking. This is an NFA to be strictly speaking, so there should be an extra state for the error.
Okay, yeah. If you insist on having arrows coming out from every state,
I'm just saying.
then yeah, you're gonna need at least 9. Blah 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 blah.
You just said lower number of states for a DFA.
What's that?
Is it lower number of states for an NFA too? Is that 'cause that's a stronger state.
Yeah.
Yeah.
Okay, yeah. Because it's just the argument.
Yeah.
Same argument holds because you. So you have talked about NFAs?
Well,
Not
not in this
Not in
class.
this
No,
class,
this
but
class
it-
is not.
611 we did.
Languages, I've taken.
Oh, and in 631.
Yeah.
Yeah. Oh, yeah, that was on fine.
So there's
Yeah.
um,
Which I misparsed actually.
something relevant. Here's a fact for you. You call it theorem if you want. There is for a given regular language L, there is a unique DFA recognizing L. It has the minimum number of states. And actually, that's probably it for that particular language. I hinted at this. You'll have programming languages for me, right? So you remember that. That's what I'm going to do today. Actually, is start writing a state machine to do lexical analysis, and there was the issue of when do you need to come up with a new state? And the answer was when you can reuse a state for a situation if they would react to any later input identically. They wouldn't need a new state. And if you apply that rule religiously, I only create a new state when I absolutely must, that's what you get.
Isn't it hard to show that though?
What's that?
I guess we did that in. I did that in EE a bunch actually.
Prove that?
No, I think we did like perfect induction on it. Perfect induction being that because it's finite output and finite alphabet, you can just write it all down and show that it's going to be the same. No, we had an algorithm for it.
For what?
For minimizing the state machine?
Yeah,
Yeah.
where you just put everything in a big
Yes.
bubble, right? A
There
big.
was, yeah,
The algorithm goes here. I actually remember now.
remembering it.
Yeah, I don't know if I should actually, after you guys rag on me so much, I'm not sure I should even come up here anymore.
We're just gonna
I'm
make fun
going
of
to
your handwriting.
erase what's it good for. So let's say you have like you have proposed states A, B, C, D, E, and F, and you have the recorded outputs given in input. It's like a Mealy or Moore machine, right? Then you put them all into this big bubble, and you check to see. So you check to see the arcs. They all should go to itself, but then you check their outputs because you can do perfect induction, given that it's it's binary for a finite string and for a finite alphabet. You can just do that, and then you break it up into
States that have the same output go to the same stage. And you just keep doing that until you can't,
until you get the identical. Yeah, until you make no more changes.
Yeah, we did that in 631 as well.
Did you?
We did. It was the one that I had to present.
Oh, okay.
Yeah,
I was so
we
I was so lost for so much of that class. Like it was way over everybody in that class that had, I guess, algorithms before me. So it was like, yeah, sure, that makes sense to me. Is that the closure thing? Yeah.
I'm not sure if I didn't quite
Yeah.
say exactly, but if you have an automaton with more state, okay, you can formalize the idea of a situation.
Yeah.
What will this automaton do for all future input?
Yeah.
And then every state corresponds to some situation. Any two states correspond to the same situation, and then you can just combine them into one.
Wasn't there the other cool thing that Hartman showed? Was there if you do the process to turn it NFP to DFA, and then, or you do it back and forth, and then it becomes minimized.
Minimized.
If you
Oh, I didn't know that.
If you take an NFA, turn it into DFA, and then turn the DFA back. Am I saying
One-
it backward?
there were two ways, and you did it one way and then back again, and it would become minimized if you followed that algorithm.
I suspect
Well,
it's
a DFA is an NFA, so that way it's easy.
Yeah.
Uh,
So I think I forget. I don't remember.
Yeah, I don't.
I'd have to read through it back
exactly,
and
but yeah,
again.
it does minimize.
There was one
There
algorithm
was
we
a way
did
to
where
make
we
it.
would.
Yeah. It's in the compiler's book.
NFA to minimal DFA.
I actually looked up the compiler's book for this part, and they did not have a pumping lemma in it, like in the index or anything.
Yeah.
No, but it's got the minimizing.
Yeah. I don't care.
There's just googling around. There's also this kind of interesting Myhill-Nerode theorem, which is actually a sufficient condition for proving that a language is regular. So you can use it to categorize regular languages.
Sufficient. Why don't you just? I mean,
Yeah, I can write it up there.
a language is regular if you just write it
What?
down.
Yeah.
Yeah.
I just copied this down to Wikipedia.
Oh, Wikipedia making.
Wikipedia knows all.
This is being recorded.
As an
boys.
undergrad, you cannot use Wikipedia. As a grad student, well, this is what Wikipedia said.
What else do you use? Yeah.
So if we let
Can I interject something on that? On code execution, compilers, JIT compilers, interpreters, it's awful. It's just terrible.
Oh, really? The
I-
Wikipedia stuff?
It
Yeah.
uses terminology inconsistently across articles, sometimes inconsistently in the same article.
Interesting.
Oh yeah. Oh, I remember.
It is fantastic for graph theory. It's fantastic for this stuff, but man, don't cite it when you're talking about compiling. It's not good.
No, I remember just trying to learn out of Wikipedia in addition to the Dragon book because I was so far like out of
And just getting
The loop.
confused.
and just it was enraging how bad it was actually. I wonder if the Wikipedia article on Square is still really bad. You used to have the Squares that has a Shalaf symbol for truncated square, T for an octagon. The square is the N2 case of the families of N hypercubes and N orthoplexes.
What is this?
This is the
This is
Wikipedia.
a condition for
What's whose?
what?
Whose?
This is the Myhill-Nerode theorem, and it's a sufficient condition for. So a distinguishing extension is if you can come up with a string such that X concatenated with C
Okay.
and Y concatenated with C. Only one of them
is a formalization of my rule when you need different states. Yeah.
Yeah.
Okay. Okay.
And then, so for the actual Myhill. Oh wait, we need to define one more thing first. Define the equivalence relation. X. No distinguishing extension exists.
So, can I make a guess?
Uh-huh.
A language is regular if there are a finite number of equivalence clauses.
Yeah.
Yeah. Okay.
And
equivalence clauses are states.
The minimum DFA that you said is exactly the number of equivalence classes.
Okay.
So yeah, I guess the what I didn't state is the Myhill-Nerode theorem is exactly the language is regular if and only if there are a finite number of equivalence classes. I didn't read the proof. I don't know. We can kind of.
Okay. So I'm a little careful there and show that that is actually an equivalence.
They say it can be shown. Yeah, I didn't show it was
Probably
either.
not too hard.
So
But you would need to show that. Yeah.
X is related to itself. Clearly, X
Yeah,
is
if it's regular,
if
there's going to be a finite number of
X,
equivalence classes just
no,
because
Y clearly
every.
Y
Oh, okay.
X.
Yeah.
And so that clearly
it's
follows.
reflexive. XRLX. There's no distinguishing extension between
Yeah.
X. That's
And then so the trick is transitive. So
is
XRLX and YRL. We won't use the. I guess we'll use W. So there's no distinguishing extension. I don't know how to show that actually. Let's see. So there's no string you can append to this and append to this. So that
if XZ is in the language,
yes.
then YZ is, and if YZ is, then WZ is,
yeah.
and vice
So
versa.
for any Z, yeah.
So,
XZ,
so there you go. Yeah.
yeah. And then following from that, YZ is a now. Okay. So the equivalence relation.
That's nice. Did you catch that? Didn't write it. The language is regular if and only if there are a finite number of equivalence
Right,
classes.
yeah.
And basically, those can be the states.
Bit over my head.
How do we relate that? So what does an equivalence class represent in respect to a DFA?
What's that?
What does an equivalence class represent, like thinking of it as a DFA?
What does it represent?
Yeah.
I mean,
And
the equivalence class here is a set of strings.
yeah,
And so,
but clearly they have some direct relation to the DFA since there's exactly the number of
yeah,
states as there are.
well, you can think of a DFA state as a set of strings. It's the strings that take you there. And so every state is a set of strings, and when you add a symbol to a string, you go to the state that corresponds to that next string. And then the accepting states The evening of them is the language. You can do anything remotely like that for context-free language. Probably not. Oh. Thank you. That's cool. It's 2 o'clock.
Throw a short, guys.
Do what you want, but I have class downstairs.
I can't.
We want to end that.
Yeah.
Chat about regular languages until the sunset.